Hey everyone, Mr. Newman here, and today we're going to learn about graphing exponential functions. By the end of this video, you should be able to identify the types of exponential functions and evaluate them and graph them. So let's get started. First of all, exponential functions have the form f of x equals b to the x, where b is a number greater than 0, or b is a positive number, and x can be any real number. That means the domain of these is all reals, because x can be any number. Remember, there are three ways to write that. You can say negative infinity is less than x, which is less than infinity, an interval notation that looks like this, parentheses, negative infinity, comma, infinity. Or you could just write the words all reals. That's because we can plug in any number, positive or negative, into that function. The range, the output, however, is only the positive numbers, because you can only get out positive numbers out of this function. We'll see this later when we graph them, how the range is only numbers bigger than 0. And that does not include 0. So that means that this point right here, this parentheses, needs to be a parentheses and not a bracket, because we're not including 0 in the range. Alright, I have for you graphed here the two types of exponential functions. The first one is called a growth function. That's because as you go into the right, it's getting bigger. And the way you can tell a growth function from the equation is that when f of x equals b of x, b is greater than 1. If b is a number bigger than 1, that means you're multiplying by a number bigger than 1 every time, and that is going to make the number bigger. The one on the right, the red one there, is a decay function. That is because the exponential function is decreasing or decaying as you go to the right. The function f of x equals b of x, the way you can tell that it is a decay function from the equation is that b is between 0 and 1. In other words, it's a fraction or a decimal that is smaller than 1 but positive. So if you multiply by a number smaller than 1, like say 1/2 for example, multiply by 1/2 over and over, that number is going to get smaller and smaller, and we call that exponential decay. So let's practice graphing these. To graph them, we're going to do the same thing we did for lines and for parabolas. We're going to make a table and then we plot the points, and we connect them in a way, connect the dots in a way that makes it a smooth curve. Now, one comment about exponential functions: the more points you plot, the better, because they can be very finicky. So we're going to plot as many points as possible, and I would say these 6 points here that we make in the table, not all of them will make it on the graph, but as many as possible. That way we can graph the function. Also notice I chose a few negative values, 0, and then some positive values, just like before when we were graphing the parabolas and the exponential and the quadratic functions. So make a table. How do you make a table? Well, we're going to plug in -2 into x. So 2 to the -2nd. If you remember from our exponential powers, that's 1 over 2 to the second, our exponential rules rather. 1 over 2 to the second, that's 1/4. And if you would rather that be a decimal because you prefer graphing decimals, that is 0.25. So we're going to plot that point at -2, comma, 0.25, because the x value is -2 and the y value, or the f of x, the output, is 0.25. For the next one, x is -1, then 2 to the -1st is the same as 1 over 2 to the second, if you remember your exponent rules. That means that our output is 1/2, and that, in terms of decimals, is 0.5. So I'm going to plot that halfway between 0 and 1 on the y, and I'm going to put it at -1 for the x. When x is 0, this is on the y-axis, 2 to the 0, well, anything to the 0 power is 1. So this is going to be 0, 1. When x is 1, that's 2 to the 1st power, and so we get 1, 2. When x is 2, we get 2 squared, which is 4. Plot that point. And 2 to the 3rd is 8. So we'll plot that point. Notice a few things. First of all, the y-intercept is 0, is 1. We also notice how these points start getting bigger and bigger really fast. The next point's going to be 16 and then 32. So those numbers get really big really fast. So that curve will typically go off the graph at the top really quickly. And especially when we have such a big factor as 2. And 2 might not seem like a big factor, but when you're multiplying it over and over, it does get very large very quickly. So I'm going to connect those dots and make that go, but you notice how steep it is vertically. Other thing is, you notice on the bottom left there, that does not cross the x-axis. That's because those numbers, if you keep going left, are going to get smaller and smaller, but never actually touch 0. We call that an asymptote. And that is why the x-intercept is none. There is no x-intercept because of the asymptote. Now I want you to draw that dashed line along the x-axis to show that the graph or the curve never touches the x-axis. And we call that an asymptote. For the y-intercept, the point is 0, 1, and that is right there. That's because anything to the 0 power is 1. Alright, I want you to try the next one on your own and answer these questions. Did you get it? Here we go. So 4 to the negative second power is 1 over 4 to the second, which is 1/16. If you're stuck on that, you could also type in 4 to the negative second in your calculator, just like that, and you would get a decimal 0.0625, which is perfectly fine for these purposes. 4 to the negative first is 1 over 4 to the first. That's 1/4, and we get 0.25. 4 to the 0 is 1, because anything to the 0 power is 1. 4 to the first is 4. 4 squared is 16, and 4 to the third is 64. So we plot those points. Notice I can't plot even x equals 2 because that's 16. That's off the top of the graph. So I'll only plot the first 4 points, and I'm going to make sure that that line is very steep and doesn't even reach x equals when x is 2, because that would be up off the graph. Now one comment, make sure, I tried not to do this, but make sure your line doesn't go back to the left or even get exactly straight up and down vertical. It's still going to the right, and it's not an asymptote there because it will continue going to the right. It just gets so steep it looks like an asymptote to us. But there still is an asymptote on the x-axis. That's why the x-intercept is none again, and there's an asymptote. So draw your asymptote on the x-axis, but there is not an asymptote, a vertical one, going up and down. Alright, for the last one, you notice the big difference here. Oops, sorry, 0, 1 is also the x-intercept again because anything to the 0 power is 1. Notice the difference here is we have a 3 out in front. And what I want to remind you of is whether you learn GMDOS or PEMDOS, remember that either way, exponents come before multiplication. And that 3, when it's in parentheses in front of that exponent, it means multiply by 2 to the x. So we need to take care of the 2 to the x first, and then multiply whatever that is by 3. Exponents come before multiplication. So let's do that. 3 times 2 to the negative second. Well, we need to take care of 2 to the negative second first. That's 1/4. So 3 times 1/4 is 3/4. The decimal representation of that is 0.75. So I'll plot -2, 0.75. When x is -1, that's 1/2, so we take care of the exponent first, and then we get 3 times a half is 3/2, also known as 1.5 or 1.5. I'll plot that point. When we do 0, remember you have to take care of the exponent first. So 2 to the 0 is 1, and 3 times 1 is 3. So this y-intercept is not at 0, 1. That's because of the 3 out in front of the graph, in front of the equation. Then we do the exponent first again, but 2 to the first is just 2, so we get 3 times 2, which is 6. Plot that point. And 2 squared is 4, and 3 times 4 is 12. And 2 cubed is 8, 3 times 8 is 24. So notice, those get off the graph very quickly, but we can still plot those first 4 points. And we connect those, and I'm going to go ahead and draw the asymptote that we know is there, because there's no x-intercept again, and the y-intercept became 0, 3 because of the 3 that's in front. Now you go, all right, well, what number is in front of the first function, for example? Well, that would be 1, right? Whenever there's not a number in front of a variable or coefficient, you can always treat it like 1. So you could think of 2 to the x as 1 times 2 to the x, and that 1 in front is the reason that the y-intercept of those, another reason why the y-intercept of those is 1. All right, thank you very much for watching.